So this week we're going to start out talking about the hydrosphere, or we will spend the entire week talking about the hydrosphere. So this is broken into three sections. The first section will be streams, the second section is groundwater, and the third section is oceans. So we'll spend the entire week talking about water, or the hydrosphere. So for this, basically you'll have streams quiz 1 on Blackboard that you'll take simultaneously. I've got a couple spots in here that you'll stop and then answer the quiz questions as you go along. So this first section of the hydrosphere is all about streams and floods. We're going to go over some basic definitions for understanding water and how water flows and how water works. So just to talk about the importance of water, why you should care about this and why you should learn about this is that we use water for a variety of reasons. Water is good for supporting wildlife. On the bottom left, we have to use it to drink and survive. So this is a drinking water treatment plant. In the middle here, we use water as a transportation vessel or mechanism. So we have a barge here that's transporting coal on the Ohio River. We use water for irrigation, for crops and agriculture. We use water for energy production, hydropower, nuclear power. Every kind of power plant uses water in some way. And then also we use water as an aesthetic type thing or for sport or recreation. So if we talk about the distribution of water on Earth, and we look at the total, if we consider 100% of water on Earth, the breakdown of that, 97% of it's going to be salty, 3% is going to be fresh. And if we look at the proportion of fresh water, this has changed now because this data is from 2007. It's about 70% frozen water right now. So fresh water is locked up in glaciers, frozen. And then roughly 20% of unfrozen water is groundwater. And then, or 30% now, 29 to 30% now of fresh water is groundwater, and then 1% is lakes, rivers, and streams. So if you look at the total distribution of water around the globe, 97% is ocean water, 2.2% is frozen in ice, 0.7% is groundwater, and then less than 0.1% is surface water. If we just consider rivers, which is probably the fresh water that you interact with most, because you see it and you drive by rivers and streams, assuming you look at them, then rivers are only 0.0002% of the world's total water. So when we talk about water and like drinking water, we don't actually have an immense reusable supply of water on Earth. So when we're talking about water, we can't talk about water without talking about the hydrologic cycle. So we have ways of moving water around the globe through different mechanisms. So water can be stored in certain locations, like in clouds, lakes, groundwater, the ocean, and in rivers. And then we have ways for water transferring from one location to another. So we could have infiltration. If it rains and water soaks into the ground, we get infiltration. We can get discharge, so movement of water underground from an aquifer, which we'll define in the next section, out to the ocean. We get evaporation. That's a way of moving water around the globe. Evaporation from land or evaporation from the ocean as well. So the hydrologic cycle or the water cycle is how we move water around the globe continuously. So based on this, you should be able to answer questions 1 through 3 on the quiz. So a second little subsection here is where do rivers and streams come from? So if I asked you to go look at your local river on any given day, what does that water come from? Where did it actually come from? So there's a couple things that it actually comes from. One is obviously rain or melting snow. So depending on the time of year, for example, it's probably going to be made of melting snow or rainfall that's fallen in the past couple of days. So we already know that water drains to a stream or a river, and then a river will be made of rain and melting snow. What we also have streams made of is groundwater. So again, that's our next kind of unit that we'll talk about. But groundwater, if you go out to the Nashua River, which is our local river, on any given day, if it hasn't rained recently, what you're actually seeing is water that used to be underground and it's seeped up through the river surface. So you're actually seeing water that was underground or groundwater that is now surface water. We'll elaborate on that more in the next unit. All right, so we have some definitions to kind of go through here. Rivers are going to flow from a high point to a low point, so they'll typically flow from a more mountainous area down to a more flat area, and then they'll move down slope under the force of gravity, and they'll move to something called base level. So base level is just where usually sea level is. So all drops of rain that fall somewhere on Earth's surface eventually flow to the ocean, and we just call that base level. There's kind of localized base levels, but the ultimate base level is what we call sea level. So we have small streams combine to form bigger streams combine to form rivers, and then once a river makes it towards the ocean, it's usually quite large, quite wide. And on average, it takes about 14 days for once water falls as a drop of rain, for that drop of water to get to the to get to the river, and then flow down the river towards the ocean. That takes about 2 weeks on average. So one more definition here is watershed. This is also called a drainage basin. It's also called a catchment, a drainage area. So there's lots of different interchangeable terms that we use to describe the same thing. But a watershed is just the total land area, usually in square miles or square kilometers, that drains to a specific point. As an example, if you have a drop of water that falls, let's say near the Gulf of Mexico, that drop of water has fallen in the Mississippi River Basin. And at the outlet where the Mississippi River Basin meets the Gulf of Mexico, the outline here shows you the entire area that drains to that point. So the entire area that's in the colors here, that is what we call the watershed. Any drop of rainfall that falls in that area is going to drain to the Gulf of Mexico. The other relationship here is that the smaller the watershed is, the smaller a stream tends to be. So this stream would be about 10 feet wide or so. But if you have a bigger watershed, more land area that's draining, more water that it can carry. So you're going to get a very, very wide river in that case. So how do we determine what separates watersheds? So they're called divides. So the map that you're seeing on the image, or the image that you're seeing on the screen here, is basically showing you different locations of different drainage divides. So the ways these work is that they divide one watershed from another. So for example, if you're on the East Coast and you have a drop of rain that falls to the right of this yellow line, that water is going to drain to the Atlantic Ocean. But let's say you have a drop of rain that falls on the left side of that yellow line, it's going to drain to the Gulf of Mexico. It'll go in a different direction. If you have a drop that falls on the right side of this triple divide peak over here in Montana, it's going to flow to the Gulf of Mexico. But if it falls on the left side, then it's going to drain out to the Pacific Ocean. So a divide basically separates different watersheds in which direction they actually flow. All right, so you should be able to pause here and answer questions 4 and 5 on the quiz and come back when you're done. So the next thing we need to talk about is drainage networks. So not all streams, or all streams usually, are part of a network. And again, small streams combine to form larger streams combine to form rivers, and then rivers can get larger and larger and larger as they flow towards the ocean. So we have an example of an aerial image of a drainage network here where we have these smaller channels. They combine, and you'll get a progressively larger channel as smaller channels combine until you get this full-fledged, wide flowing river. So how do these form? They form over millions of years as water erodes away the land. So anytime it rains, rain erodes, carves rock away, it weathers away rock, as we already discussed. And then as it carves away rock and carves away land area, you will get this preferred drainage area, this preferred pattern of flow over millions of years, and you create a drainage basin over that amount of time. So just to give you an example, the Amazon River used to flow a different direction. So we have 3 maps here of South America in the past. And in the past, before the Amazon River Basin developed, the streams in that area would flow towards the west. As time progressed, it reversed direction, so the rainfall started carving out these channels, and then the water, instead of flowing to the west, started to flow to the east in this direction here, out to the eastern Atlantic Ocean instead of the Pacific Ocean in the west. So not all drainage patterns look the same. There's different types of drainage networks, but typically, since water will follow the path of least resistance, as it does so, it'll form these patterns on the surface that looks like different types of networks. So you can get something called a dendritic pattern. If you are a dendrochronologist, you study trees. So this one looks like tree branches here. Typically, if you have uniform rock coverage, so let's say you have an entire area of sandstone, it's all going to erode at the same rate. So you're going to get kind of a tree-like drainage pattern that will form. Let's say you have a volcano or a hill. That volcano, as rain falls on that volcano, water is going to flow down all sides of that volcano. So you'll get something called a radial pattern where streams radiate around from the center point. A rectangular pattern is usually if you have bedrock like limestone that is kind of broken apart and with cracks, and water will follow these preferential cracks that will form in the limestone, and you'll get a rectangular pattern. And then lastly, you can get a trellis pattern, which looks like this one here on the bottom right. That's typically when you have different types of rocks in a small area. So if you have a very strong rock and then a very weak rock right next to it, the weak rock erodes away more, the strong rock stays behind. So then you kind of get this trellis pattern that will form. So your next two quiz questions is based on these images that you see here. What is the type of drainage network that you see in each image? So moving on, just to finish up a couple more concepts here, if we're talking about factors that influence how much a stream flows, so how much water, how much quantity of water it has in it, or what that stream looks like, there's a couple factors that we'll talk about that affect what a stream looks like and how it's flowing. So one is gradient. Gradient is just slope, so it's the slope of the channel. If you have a very steep slope, a stream will look totally different than if you have a very flat slope. If you have a flat slope, streams tend to kind of snake around and meander. But if you have a steep gradient, then you're going to get waterfalls, very rocky, bouldery streams. So they'll look very different just based on the slope that you have in that area. Just to give you an example, if you have a steep slope stream, it's going to have a lot of boulders in it. You'll have like white water conditions. It'll have a slow velocity, so the water looks like it's flowing fast, but it's not actually flowing as fast because it's got a lot of obstacles in a rough channel to kind of navigate around. And then a low gradient or a flat slope river or stream will look more like this one on the right side. So it's wider, it's deeper, it's actually flowing faster because it doesn't have any obstacles to kind of slow down the flow. We also have discharge. Discharge is the amount of water that's basically flowing in a stream at any given time. It's a volume, so how you get that is width times depth times velocity or speed. So for example, if you have a hypothetical river that's 2 feet, or we'll say 2 meters deep, 5 meters wide, and it's flowing 10 meters per second, we can calculate what we call the discharge, which is usually in meters cubed per second is the unit, or you can have feet cubed per second. So your quiz question here, looking at discharge, again, the volume of water passing through a given point in 1 second. What is the discharge of the stream with the numbers that you have here? So what we'll talk about in the next lecture is looking at mechanisms of flooding and then what we can do about flooding over the next couple of lectures. So I want to point out that discharge is always changing. Discharge every minute to every 30 minutes is going to be a different value because there's always different amounts of water that are flowing past a location. So that could also be the difference between something like a nice dry condition here on the left side, which we call something called base flow, versus a storm flow, when a storm has recently happened and you're in flood conditions here on the right side. So my final point here is that discharge is always changing, but we can kind of calculate it at a pinpoint in time or a snapshot in time to get an idea of how much water a river is holding.